Hey, this is Angela Rasmussen from the University of Utah Electrical and Computer Engineering Department, and I wanted to go over the RLC derivation for a parallel configuration. So we're going to look at trying to understand the derivation of the second order differential when we have a parallel configuration. So here we can see a circuit, and the switch is closed at time equals 0. So at the final time, which is where we're going to do the derivation, is going to be with that wire across R2. So it's going to basically bypass R2, and so we can ignore R2. So our circuit ends up looking like this, where we have the R2 is being ignored. Put it down here. So in the circuit, as you all know, I like to do node voltage. So notice that VC, which is the voltage across the capacitor, is the same as the voltage at this node. So I can call this node actually VC. And then I have current in this branch is going to be VC minus V naught over R1. The current in this branch is just IL, and the current in this branch will be IC. So there's my node voltage equation. And now I also know the relationship between IC and VC. So IC is C dVC dt. And I also know that VL is L di dt. And so we can use these relationships. So IL and IC. So IC I can immediately substitute in, and so I'm going to have now an equation with VC in it and dVC and dt. But to get IL, I notice here that if the only way to get IL from this would be to differentiate or to integrate, which is not going to be helpful, and substitute in then IL. Same thing for VC itself. Like if I try and write VC, I'm going to have an integral. So I want to try and see, is there another equation that I can get here? And so I know that I can also do a voltage loop. And if I take a voltage loop through the inductor and the capacitor, that gives me a relationship between VL and VC. And so if I take a plus ILR3, a plus VL, and then a minus VC, that equation will give me plus ILR3 plus VL minus VC. And here I can substitute in VL, and I have VC in terms of an ILs. So substituting in VC, I bring VC over to the other side. That becomes a positive. And then I have ILR3 plus VL, which is L DIL dt. And so now it looks like, okay, this is going to be easier to substitute that in for this VC here. And so if I do that, I get ILR3 plus L DIL dt all over R1, and then minus V naught over R1 plus IL. And now IC, I can do a replacement of C dVC dt. And if I differentiate this, I'm going to have VC is going to be ILR3 plus L DIL dt. And so now I can kind of combine terms and differentiate this out fully. So if I differentiate this out, this becomes I'll just multiply them out first. So I1 R3 over R1 plus L over R1 DIL dt minus V naught over R1 plus IL plus C, and then this becomes R3 out in front, DIL dt, and then this is a LC d squared IL over dt squared. So now I want to get rid of the LC, so I can multiply both sides by 1 over LC, just so that we have no term in front of the d squared IL dt squared. So I'm going to just bring that over to the left side. So this is my d squared IL over dt squared. LC's will cancel. And now I want to combine all of the first differentials. And so I'm going to have a term here. So this is the L will become canceled out with the L on the bottom. So this becomes 1 over R1C. And then the other term is here, and then the C's will cancel, so I'll get R3 over L and DIL over dt. And so I've taken care of this term. And I've taken care of this term, and I've taken care of this term. So now I have the I1, so I have R3 over R1 LC, and then I also have this term is just 1, so that will just be a 1 over LC, and so this is all multiplied by IL, and then I can take the constant over to the other side, so I have a V naught over R1. And now I have that this term I could call A, this term I can call B, and this term I'm going to just call C. And I can rewrite this in terms of sorry, just making sure I wrote that correctly. And then I can put X is equal to IL. And so I can kind of rewrite this in terms of like the primes. So if you remember, or if you haven't seen it yet, in math you can do a differentiation is just a prime. So X prime would be the first differentiation, and then X double prime is the second differential. And so this would be X double prime plus AX prime plus BX is equal to C. And then this is going to be the form that you've seen more from the math classes. So this is a second order differential. And to solve this, you first solve it as a homogeneous equation. And so that means that you're going to set it equal to 0 first. And then you're going to either make a guess at what the solution is and then substitute it in and solve for that. Or you can, and then once you get that solution, that would be considered the homogeneous solution. And then you're going to find the particular solution when you've set it equal to C. And so then you would add those two together for the total solution. And so what we know is that it is already, and we know this because we know the answer, is that X is of the form AE to the ST. So now when we differentiate that, we bring down, remember from an exponential, you just bring down the S portion of it. And so I'm differentiating it with respect to T. And so it becomes this for the first differential. The second differential becomes S squared. And now substituting that back in, my equation looks like this. And I can see that I have an AE to the ST. And remember, I'm solving it first as a homogeneous equation, so that would be set equal to 0. And then I want to solve for these roots. And the roots of this equation is going to be the homogeneous solution, so it will give us the roots. and then we would add that to the forced function one, which would be the particular solution. And so I can pull out here an AE to the ST, and that gives me S squared plus AS plus B. And then I can solve this as a quadratic. And so this becomes that S is equal to this minus B here, plus or minus the square root, sorry, not B, that is A. So the variable in front of that second, just the plain S, and so A squared minus 4 times 1 times B over 2A, or 2 of the variable in front of the S squared, so over 2. And so what I do here is call alpha, which is A over 2, and then I'm going to call omega naught as the square root of B. And so remember, 2 can also be written as the square root of 4. So 2 is also the square root of 4. So if you have a minus 4b over the square root of 4, the 4's cancel. So I can rewrite this S as a minus alpha plus or minus the square root of alpha squared minus omega naught squared. And so this is where we get our equation for the roots of the system. And so this is our roots that solve the equation. And then what we can do from here is then look at the other solutions for the particular solutions, and depending on alpha and omega, you're either going to get overdamped, underdamped, or critically damped.